Hello, ladies and gentlemen. Thanks for coming back again for another installment. Yeah, this is called Hess's Law. It's really simple and pretty short, too. I mean, it can look crazy and confusing, but let me try to simplify. You might remember in math, when we're trying to solve for an unknown, a variable, we might have a system of equations. We do some manipulation to those equations, add them together, and try to solve for one of the unknowns. In a similar way, pretending like these are equal signs, but they're not. They're arrows. It's a chemical equation as opposed to a mathematical equation, but nonetheless, let me say that these two reactants make these two products, and these two reactants make this product, and these two reactants make this product, and they're three separate chemical reactions. But what I'm claiming is, in Hess's law, that you can take those seemingly separate, and they are separate chemical reactions, and I can, what Hess's law says is I'm allowed to add them together in a step-by-step combination, so to speak. And anything that occurs on the left-hand side compared to anything that occurs on the right-hand side is just cause for cancellation. So take that same thing and look at what I wrote here. I saw an L and an L on the left and the right, and I canceled them out. An N and an N, whatever it is, chemical species, on the left and the right of the arrow. And finally an R on the right and an R on the left, and they cancel. So what's left over? Well, I have one C species, two M's, two capital M's, and one Q. So even if I never could do the chemical equation, I can talk about C plus two M's reacting to give a Q, and this seems contrived. Like, why would I want to do such a thing? Well, oftentimes there are situations where you can't really do that reaction, but you might want to know what the heat associated, the energy change associated with that reaction might be. So what I'm also allowed to do is I took that same system of equations, called this is the heat change associated with reaction 1, heat change with reaction 2, heat change with reaction 3, and so if I add them up and I see cancellation, then this reaction, which I may or may not ever be able to do, or even if I can do it, I might not be able to measure this directly, but if I combine these in the appropriate order, which just means to add them up, then lo and behold, I've discovered the change in enthalpy, or the heat change with that overall reaction. And another thing that we'll have to do, in very similar to math, is for any one particular equation. So I took the first equation from above again, called it delta H1. What if I flip that backwards? What if I said L plus N gives C plus M? Well, I can do that. Whether or not it's difficult to do in practice is a different question. But the theory is that this delta H1 changes to the reverse. So if this was positive 100 here, it changes to negative 100 here. Or if this is negative 500 here, it changes to positive 500 here. So just take the reverse of it. That kind of makes sense to me. Also, if you're multiplying by a particular constant term, maybe you want to multiply it times 3 straight across for a particular reason. And that particular reason would have something to do with trying to get something to cancel from the system of equations. I must also take my heat number times 3, or take it times a third all the way across, and now I divide by 3. So I call the equation that I'm shooting for the target equation, the net equation, the total equation, and that's usually given. So let's say try to find the heat associated with this reaction: carbon plus water, carbon solid plus water vapor, carbon monoxide, and H2 gas. And you'll almost always be given the equations that you need. It would be an even more difficult question to say, well, go find your own equations and figure out how to add some of them together to find this total heat. Well, that's kind of mean. I wouldn't do that. But what I would do is say, I know that I can use these 2 or 3. Sometimes it's just 2 equations. Sometimes you need 3 equations. In a really bad question, you need 4 equations or more. But 3 at the most, I would say. Here's an equation, gives off heat, exothermic. Here's an equation, gives off heat, exothermic. Here's an equation, gives off heat, exothermic. Not too surprising, because most reactions like to give off heat. But these numbers are given to me, or equations and numbers are given to me. Now my challenge is to try to get these, to manipulate these to add together to give this overall reaction here. So this is an art form. let me rephrase that one more time. I want to get this, but I have this. So in this first equation, I see carbon listed first, and this is kind of an art, so bear with me. Carbon, one carbon. Nowhere else in this whole mess do I see a single carbon or a carbon all by itself. So I'm thinking that this first equation is going to be good just to be left alone. So I'm going to rewrite this first equation like that. But anyways, let's go on. I just rewrote it. In the next equation, I see carbon monoxide. And I look around and I see no other carbon monoxides other than my target equation on the right-hand side. So I'm thinking I may have to turn this equation for this carbon monoxide as a product, so that's on the right-hand side. But not only that, there's a 2 in front. And that does make a difference, because if I have 2 carbon monoxides, there's twice as much heat is associated with as with 1 carbon monoxide. So not only will I turn this one backwards to get the carbon monoxide on the right-hand side, but also take it times a half or divide it by 2. So I'm also going to have to, take this delta H number and divide it by 2 as well. Having trouble with there we go. What about this last one? H2 and O2. I see I do see an H2 up there. What do you know? I see a water here too. Interesting. Well, let me guess this. Since I have H2 on the left here, H2 on the right here, similarly, I'm going to think about turning this equation backwards. But again, since there's only one H2 up here in my target equation and 2 H2s in my given equation, I may have to take this whole thing, including that number, divide it by a half. So look what I did. Look what I did. There we go. Just as I was saying a minute ago, I left that one alone. Turn this one backwards, and that's the negative. Take it times a half. Same story for this one. Take it backwards. Take it times a half. So that number didn't change. This number, I'm going to take it times a half and change the negative, take it divided by half. So that manipulation is going to look like this. And then I draw a big, large, fat line underneath and say add them together. Now, I could just add these numbers up, and I will. But I also am curious to make sure my cancellations are all going to work out to give my target equation. And lo and behold, one carbon dioxide cancels carbon dioxide. 1/2 O2 molecule, 1/2 moles of O2, 1/2 moles of O2, full mole of O2 on the right-hand side, and mole of O2 on the left-hand side. So lo and behold, 1 carbon left over, 1 water left over on the left-hand side, H2 on the right-hand side, and carbon monoxide on the right-hand side. And so that is it. That's my target equation. And I take the numbers and I add them up. This looks endothermic, so it's positive, yeah? No. Did I forget my negative? No, it is positive. Oh, yeah. This was negative, but I switched them backwards. So, yeah, all right, cool. Endothermic. Let's try another one. And if you're really brave, you pause the video and try it yourself. Try to manipulate these equations to get this equation. I don't know. Yeah. So, and this one has C3H8 on the left-hand side, but my target equation has C3H8 on the right-hand side. So what should I do to this first equation? Oh yeah, flip it backwards. So that I want to get C3H8 on the right-hand side. Flip this backwards and rewrite it. Carbon, cool. The second equation has carbon on the left. My target equation has carbon on the left, but there's a 3 there, so I'm worried about that. So I better take this times 3, this times 3, this times 3, and this times 3. H2 on the left, H2 on the left, that's looking pretty good. So why don't I just use this H2 right here, except again, since I have 4 H2s here and 2 H2s here, I better take this times 2, take it times 2, take it times 2, take it times 2. And I did. Took it times 2. Took this times 3, and I flipped that first equation backwards. And if I'm just double checking to make sure it all adds up correctly, and I should, again, I take the negative of the first one, 3 times the second one, 2 times the third one, and try to add them together, verifying, illustrating, proving. 3 carbon dioxide left, 3 carbon dioxide right, that cancels. 4 waters left, 4 waters right, that cancels. 5 O2s, 3, 4, 5 O2s, those cancel. And I'm left with target equation. And indeed, I just took those algebraically, added them straight together. Take these and add them up. Phew. Are you up for one more? Sure you are. Why not? Yeah. So given these heats of reaction, This reaction gives off this much heat. This reaction is actually endothermic, takes in that much heat. Try to find the heat for this equation. So, this should be water gas. I get kind of lazy with that sometimes, leaving off my phases, but I shouldn't. Here I have two H2s on the left. This is going to be a tough one. 3 H2s. So how do I get from 2 H2s to 3 H2s? I think I'm going to have to get a fraction going here. Check out what I did. I took 3 halves of this. Take 3 halves of this, 3 halves of this, 3 halves of this, 3 halves of this. That gives me this equation. And then I looked at this one and saw O2 on the left. There's no O2 in my target equation. Let me go over here. O3 on the right. O3 on the left. So if I have O3 on the right of this given value with this given equation, I want to get O3 on the left for my target equation. So I'm going to turn this one backwards, and I'm going to get rid of that 2 by dividing by 2. So that's what I did. I turned it backwards. Yeah, right. I think I did. Turned it backwards and multiplied by a half. So that's backwards, negative, and a half. So that's what I got when I did that, performed that math. So 3 moles of that, 1.5 moles of that, 3 moles of that, this much heat associated with that, 1 mole of this, 3 halves of a mole of that, gives off that much heat. Add the equations together, see what you get. Luckily, the 3 halves of a mole of O2 on the left cancels with 3 halves of a mole of O2 on the right, and there's no O2 left over in my target equation, and lo and behold, I get another heat number. Whether or not I can do that in real life. Well, Hess's law takes some practice, so crack open a book, come to lecture, and I'll see you soon. Thanks, guys.